All right, everybody, I'm going to go ahead and get this going. I want to make sure all the speakers have as much time as possible. If you're here for the UFS application, air quality, atmospheric composition, aerosols, then you are in the right place. Just so everybody knows, if you are online or in person, if you're in person, pay attention. I'm going to be sitting over there kind of in that angle. And I'll have some time cards so you know where you're at. So make sure you look up every once in a while. And if you're online, I'll probably jump on the mic and I'll say like 3 minutes, 1 minute, or I'll say you're at time. And I'll try to do it in between your slides or at breaks, so that way I'm not interrupting your flow. But just keep that in mind. Pay attention to the time. We want to make sure everybody has as much time as possible. With all that being said, I'm going to go ahead and hand it off to one of our chairs, Ravon, so if you want to go ahead and take over.
Yeah, thank you, Aaron, for the introduction. Welcome, everyone, to our air quality session. We have a busy schedule. The first presentation will be given by Barry Baker from EMC. He will talk about the CAD/CAM model development.
Hey, Ravon, can everyone see this?
Yes, we can. Yes, we can.
Okay. So yeah, I want to talk about CAD/CAM version 2, which has been going on. I didn't list everybody here, but there's a long list of people that's involved in this, and so sorry if I missed out here. So, just to kind of kick it off, what is some of the things that we're trying to answer in atmospheric chemistry? This adds all kinds of things to societal challenges related to weather, air quality, smoke, and climate. And so, what are some of the things that we can do? Can we improve air quality predictions and quantify their impact on weather forecasts? Can we do a better job of quantifying emission sources and what it's contributing to poor air quality, et cetera? So I just kind of wanted to give a frame of why we're doing this. And so in the current UFS air composition structure, it's kind of scattered all over the place. There's multiple applications that are doing similar types of things. So in this case, we have RFS smoke and dust, which is to be implemented early next year. We have GCAS version 1, which should also be implemented next year. And then we have the UFS AQM. So this is the full complex regional air quality model that forms one part of the National Air Quality Forecast capability. So as you can see, we have multiple different applications, all using their own code throughout the UFS, and they have varying complexities from extremely simple, just passive tracers to simplified bulk aerosol approach to complex chemistry. And so one of the things that we wanted to do is to create something that kind of unifies all of these things. And that is what we're calling CAD/CAM, or the configurable atmospheric chemistry. So the idea is that this will store all chemistry related code in one unified location. It'll be flexible and configurable, meaning that people can choose their own gas phase chemistry and aerosol schemes and configuration depending on the complexity that we need. We're also building this system out to link to external collaborators in code, mainly through at a process level rather than through infrastructure level. And so if we map this out from the previous slide that I showed, where we have different applications, arrows in blue are for aerosols and in red are for gas phase. And you can see that these things map all over the place, right? So we need a component in the UFS that's flexible enough to handle all of these complexities. So the goals of CAD/CAM is one, we created there's a CAD/CAM repository. So this is at the UFS community GitHub page. increase the efficiency in our code development. And one of the ways that we plan on doing this is reduction of dependent libraries. We want to unify all of our composition in code to make that flexible system. And there's a bunch of things here, but basically we want to leverage the ability from our to be able to advance NOAA's mission for the R2O and O2R activities. And as part of this, I have a talk later on that will talk about unifying the emission processing with Nexus. So stay tuned for that. And then, of course, just to plug in here, but we also developed the Melodies Monet software that unifies model evaluation for atmospheric chemistry across all of these activities. So let's talk about the CAD/CAM core. So this is the core of CAD/CAM version 2. It's designed to be, the core is meant to be the foundational infrastructure for all of the processes. And it has multiple different pieces to it. So we have the state manager, which basically acts as the central data container in field management. We have a column virtualization technique, which I'll talk about in a little bit. There's the diagnostic system, which provides the comprehensive output and monitoring. So this is also how we are applying the emission tendencies or process tendencies to affect our chemical state. There's a robust error handling system developed in here so that we can track and create and understand what's happening as the system progresses or fails. And then we've also built in this flexible configuration management system that allows everything to be defined through YAML files. We can have multiple YAML files for different processes or different attributes. So for instance, there's a overall configuration, and then there's, for instance, a species configuration where we can actually define our mechanism and species. So I wanted to talk a little bit more about our core states. So the state container really is like the one-stop shop for all of our states. And so you can basically interact with the state container and you can get all of these different types of things. So you can imagine like in the meteorological state or met state, there you can get your temperature, pressure, wind, etc. The chemical state, you can get all of the species concentrations, the metadata, reaction rates, those types of things. The grid manager handles the grid and the column iterator techniques. Error management's pretty self-explanatory, and the diagnostics allow for basically dynamic registration of diagnostics. So if you turn a process on or off, you can add or drop diagnostics through the system. And then, of course, the configuration manager, which handles all of the configuration files that we need. So I wanted to talk a little bit more about the column virtualization process. So the idea is that this gives a flexible and transparent way to be able to take a 3D or 4D atmospheric variable and push this down into 1D columns. What this means is that it creates a very easy way for scientists and developers to add new processes without needing to know the full grid structure. They can work in a single column or even a box model if it's a 1D process, or basically like a surface process or something like that. It can basically be a box model, and the column virtualization allows you to do that because it can do a couple things for us. It reduces the memory pressure, so only one column is in memory at a single time for a given process, and then it also enables efficient parallelization because then we can apply OpenMP or MPI across the grid uniformly across all of these processes that are taking advantage of this. So it's a way to basically inherently add OpenMP and things to help speed up our code.
2 minutes.
Thank you. So the next thing that we've done is we've created this process generator. And so what it does is it allows scientists to more readily integrate code into the UFS. So a lot of these things end up being boilerplate. And so the interface and things like that are all generated for you, including tests and documentation, all of those things. And if you're interested, please email me, and I'll answer more questions about this. And so how the process is run is that, basically it loads the configuration, it sets up the column processes, it adds any meteorological variables that needs, and then it creates these diagnostics and applies those. It applies the tendency to the chemistry scheme. So the idea is through the process generator is that we take something that should take weeks and move it into days to be able to integrate. And it standardizes everything. Everything is built in. There's auto-generated test suites, as well as complete API docs generated all from essentially a configuration file that basically sets up the entire infrastructure. So just in summary, we've been developing this CATCAM version 2 and CATCAM system through the infrastructure bill funding. CATCAM aims to unify and improve atmospheric chemistry modeling. The idea is that this will store all the chemistry-related code into our systems, into a single system, and we've worked really hard to simplify the maintenance and enhance research collaborations. We made it easier for scientists to integrate code, and we plan on integrating this into the UFS very shortly. We're soon to open a PR, and the initial target would be through NUOPSI and CCPP integrations. So that'll be either as a separate component or within the CCPP physics package. And the interesting thing is we could
We're at time.
potentially do both at the same time. Thank you.
Thank you, Barry. Unfortunately, we have to move on. The next presentation will be in person. It will be given by Li Zhang. Li is affiliated by NOAA Global Systems Laboratory and Sea Boulder Series.
Sorry. Good afternoon, everyone. Today, I would like to talk about the fire aerosol prediction in NOAA's global aerosol system and its impact on S2S, subseasonal to seasonal forecasting. First of all, I would like to acknowledge all the co-authors from NOAA OAR Labs, EMC, and George Mason University. So as well known, unfortunately, this year, from January 7th to the end of January, there are 14 destructive wildfire affected Southern California, like Los Angeles and San Diego County. And you can see a photo here. This is a photo taken by one of my friends live near Pasadena in his front yard of this eastern fire. And also, since this year till the end of last month, there are more than 46,000 wildfires happen and burn over 4.1 million acres in the United States. And this figure shows the GSL real-time prediction by using UFS scan, and you can see the Los Angeles fire impact here. And this is the prediction in January 8th. So now we know with this wildfire activity projected to increase in the United States and globally, concerns are growing about impact of fire aerosols on weather forecast, S2S prediction, and even the seasonal outlooks. So advancing the fire weather prediction and improve our understanding of fire aerosol impact will strengthen NOAA's air quality forecast, providing more accurate and timely early warning guidance to support effective management strategies. So currently, we know that at NOAA, we have like 2 global chemistry and aerosol forecast systems under development. The first one is the UIFCW25, which is the configurable atmospheric chemistry model, the CAD-CAM that's Barry introduced just now, that's coupled with UIFS system. And here I will just focus on the aerosols module used here. And the aerosol is based on the current operational gas aerosol version 12 with some update performed by GSL in the last several years. And this model has been used CCPP as the infrastructure, which is not like the new OPSI in gas version 12. And Jian will give a talk later to talk more about the AN4 implementation recently that we did. And the second one is the GCAF's version 1, the Global Chemistry and Aerosol Forecast System. And the difference between these two models in the aerosol scheme is the GCAF's version 1 is using the NASA Go card. So it's the second generation NASA Go card. Well, both these 2 models are using the same dust function scheme developed by ARL. And one of the big milestone in GCAF's version 1 is the JEDA-based aerosol data assimilation capability has been implemented. And this model is planned to be in operation next year. So before showing the fire aerosol prediction, here I would like to introduce some updates that we did about the implementation of inline large-scale wear removal and the aerosol-aware indirect effect into Thomson microphysics scheme for GOCA aerosols. We know that since the GAFS aerosol 12, we already implement the convective wet deposition and convective transport for aerosol from the aerosol model into the SAS scheme. And why we would like to do that? Because normally the convective wet deposition and large-scale wet deposition is in the chemical model or aerosol model. They are using its own scheme, which may introduce the discrepancy when using different aerosol or chemistry schemes. So currently, by implementing this inline large-scale wear removal process into the Micron-Thomson scheme based on the existing wear removal process for ice-friendly aerosol and water-friendly aerosol, and this can help to ensure that aerosol removal is physically consistent with the model's cloud and precipitation process. And here is an example. If just look at this UIFCW model, this is the cyclone run and this is the S2S run. It's using an old large-scale wet deposition scheme from the Wolfgang. And if we would like to get a good S2S prediction, and this is the AOD bias with respect to the MERA2, but we cannot get a good a prediction for cyclone run. However, by implementing this large-scale wear removal process into the Thomson microphysics scheme. Now, for both of these 2 models, we can see the consistent bias in cycling run and S2S run. So, and the other important things, before we implement the aerosol awareness indirect effect, it would be much better to have this inline large-scale wear removal system to keep all these things consistent as the ice-friendly aerosol and water-friendly aerosol. Before showing, here, this is the fire aerosol AOD bias compared with MERA2. Here, I show 3 experiments because there are a lot of discussion that's how importance of radiative feedback from aerosol and how importance of this indirect feedback. So I would like to give an idea about the result. So the top one is that it's the same as the UFS weather model. That's the aerosol feedback is coming from the MERA2 climatology. And the left bottom one is that we turn on the aerosol radiative feedback from the coupled aerosol model. Here is NASA GoCar because this is GCAF's version 1. And the right bottom one is based on that, we also turn on the aerosol indirect feedback. And the result shows that inclusion of this online predicted aerosol for radiative feedback can reduce fire AOD bias over higher latitude in Northern Hemisphere. And at the same time, if you also include the indirect feedback, it can further remove these positive bias over higher latitude. So we got the same conclusion when we doing this experiment for UIFCW model. Even though these two models, they are using different aerosol scheme, but they get the same conclusion. That's both the GCAFs and UIFCW show consistent impact of aerosol feedbacks in this radiative feedback and indirect feedback. So we also performed an experiment, sensitivity experiment using UIFCW to quantify the fire aerosol impact on weather. And this is the experiment that we get a difference between with fire emission run and without fire emission run. And the left one is that we only turn on radiative feedback, and the right one, we also turn on the indirect feedback. Now we can see that when the radiative feedback are included, fire aerosol exhibit a cooling effect across Central Russia and Asia, while causing a warming effect over the Western US and Central Canada. However, if we enable the indirect feedback, it shifts fire aerosol impact from cooling to warming over Alaska and Central Russia, and from warming to cooling over Eastern North America. So the previous run is a single year in 2016. Here, I would like to show 6 years average about the aerosol feedback on AOD prediction. In the top one, there's no radiative feedback from couple model. It's the same. So we can see if we turn on the radiative feedback from the couple model of GoCar, the AOD IMSE has been reduced over Eastern Europe. And based on this, if we also turn on the indirect feedback, we will see a further reduction of the IMSE over North America. And how this would impact on weather? Here is, let's look at the impact on cloud fraction bias and SST. Now we can see the radiative feedback reduced global cloud fraction by 13%, while adding indirect feedback achieved further like 28% reduction of this cloud fraction bias. For SST, the aerosol indirect feedback can contribute warming over the North Pacific Ocean and helps reduce global sea surface temperature bias too. The third column. Yeah, and the other challenging in the S2S prediction of fire weather is how to estimate the fire emission in next 35 to 45 days. I will not go through the details of this slide since there is a poster by Gondola Frada there. If you are interested, please stop by to see how we predict the fire emission in next 35 to 45 days for S2S prediction. And here's the summary, and I will stop here and leave some time for questions. Thank you very much.
Yeah, we have time for a couple of questions. Maybe let's start. Is there a question online? No? Okay, here in the room. No question. Okay, thank you, Lee. So next presentation, I'm not sure if this will be remote, will be given by Yin Peng Wang, I believe from EMC. The affiliations are not shown on the abstracts. Is it virtual? Yeah, okay.
Yes. Hi, can you see my screen and hear me well?
Yes, we can.
Yeah, we can hear you.
Okay, great. Thank you. Good afternoon, everyone. My name is Yaping Wang from SAIC at NCEP EMC NOAA. Today, I'm going to talk about the JDI-based data assimilation for the NOAA's Global Chemistry and Aerosol Forecast System, GCAFS. So before I start, I'd like to acknowledge my colleagues listed here for their great efforts in the development of the GCAFS system and the DA system. So GCAFS, as you may already know, that it will be begin operations in the 2026, and its aerosol modules incorporate NASA's GoCart model. It has 15 aerosol species: dust, sea salt, black carbon, organic carbon, and sulfate. So for the first time, GCAFS include a global chemistry and aerosol data assimilation system, GCDAS, and it will use the JDI infrastructure. So the analysis of the GCAFS comes from two parts. the atmospheric analysis from GDAS GSI in the global forecast system, and then the aerosol analysis, this key part from the GCDAS, using JEDI-based 3D var F-GET method. So the aerosol analysis will be on C384 resolution. It updates 14 aerosol species using the AOD CRTM operator. The DA system will assimilate VIA's aerosol optical depth product from polar orbiting satellites, SNPP, NOAA-20, and NOAA-21 satellites. So as shown on the right-hand side, the cycling workflow shows that GCAFs update the analysis every 6 hours, and then GCDAS will forecast for 6 hours and move to the next cycle. So every 12 hours at 0Z and 12Z, GCAFs will launch a 5 days free forecast every day. So I will mainly focus on the DA system now. So the observation quality control, we only use the higher quality observation within 6 hours time window. So the ops will be thinned or super opt approximately to the C384 model resolution. There's a domain check that will discard observations near the polar region, and a bounce check to make sure that the observation values are within 0 and 5. There's also a background check that will inflate the observation errors by 3 times if the departure between the observation and background is too large. We also plan to implement the variational bias correction. So the BC will be applied to the VS NPP AOD product, and the observations from other platforms will work as the anchor. So as we all know that the background error covariance construction is a key to the data assimilation quality. GCDAS implement a flow-dependent B matrix, specifically that the diagonal of the B or the standard deviation of the aerosol species are estimated based on background. So as shown in this figure, that for each grid point, its neighboring grid points are used to compute the aerosol variance as a proxy for the uncertainty at the grid point. And we also have the standard deviation tuning ongoing using the rescaling factors that vary with aerosol species, land, ocean, and latitude. There is a spatial correlation length scale set in B matrix, so it is 300 kilometers in horizontal and 20 levels in vertical. B matrix is applied by the model called Sabre in JEDI. So here shows the results from one of our GCDAS background error tuning experiment. The cycling experiment started at the end of September 2023 from a 15-day spin-up, and the GCDAS 6-hour AOD forecast is verified against the CAMS analysis data. For reference, we also compute the difference between the Merit analysis and the CAMS analysis. The figure shows here the total AOD verification and the sulfate AOD verification. So the blue line is the no DA wrong, and the red line is the GCDAS data assimilation wrong, and the green one is the Merit2 data. So you can see that DA helps to clearly reduce the RMSE of the total AOD, and Merit2 has a lower RMSE. But this is not surprising because the Merit2 and CAMS are both analysis, and the GCDAS data here is a 6-hour forecast. And also you can see the sulfate AOD. It seems that the DA has a negligible impact on the sulfate AOD, and also DA seems to push the AOD value too high from this bias line. And but we noticed that near the last few cycles that the GCDAS 6-hour AOD forecast RMSE seems nearly as good as the Merit2's. Here is the verification for the black carbon. So in the first few cycles, DA again helps to reduce the RMSE, and then its impact seems minimal. This is probably because the values of the RMSE are quite small here, so there's little room for the DA to improve the BC accuracy. And for the organic carbon AOD verification, you can see that the DA helps to reduce the RMSE throughout all the cycles.
All right, so we're going to switch gears a little bit.
For dust ALD, here the RMSE of the ALD forecast is largely reduced by the data assimilation. So for many cycles, the RMSE of the GC dust forecast is as low as that of the Barry 2. And for CSOT, we didn't see much improvement for the first 6 weeks, but then you can see that the DA helps to reduce the RMSE. So we further verified the against the AirNet observations. As shown on the top left shows the bias and the RMSE from the DA and no DA experiment. So the bias is similar, but you can see DA has lower RMSE. And an average of the data of 3 months cycling experiment, we found that the RMSE is reduced by about 10% by data assimilation. And the right-hand side is the absolute error difference map between DA and no DA. And the red means that DA is better. And the blue means DA is worse. So we can see DA almost improve the accuracy of total ALD everywhere except some sites of over the southern eastern China. Similarly, we did a total ALD verification against the multi-satellite retrievals. So bias is similar and RMSE is reduced. And now you can see that the RMSE of the ALD is reduced by about 13% globally by data assimilation. And the map here again shows the error difference. And you can see the most significant improvements are over the dust regions, over ocean, and over some fire regions. Here are some quick QC experimental results, and the results is verified with CAMS. So first is the observation thinning or superorbing method. So we can see that it looks like no DA and DA with thinning observation has a little bit low bias total ALD, and the superorb push the ALD value a little bit higher. And the difference of mean absolute error shows that the thinning, the DA with thinning reduce the mean absolute error about 15%, but superorbing further reduce the mean absolute error.
Yeah, 3
We
minutes.
also tested the VARBC. Okay, thank you. VARBC with and without VARBC test. So that we found that VARBC has limited impact on total ALD, but helps to reduce the error of the sulfate by about 5%. We also how the DA impact the free forecast? Here we used the 5 days forecast from over 100 initializations and verified them against the CAMS. So the red and the blue, red and black means the DA and no DA experiment. So the dot means that their difference is statistically significant. As you can see that the total ALD, the reduction in the RMSE by DA is significant for more than 4 days, and the major improvements is in the dust and in the OC. So summary here with DA, we see that the RMSE is reduced by more than 10% verified against the CAMS reanalysis and other observations. And individual species improvements are variable. We see larger improvements in dust, and also in sea salt is improved after 6 weeks spin up. And superorbing QC can further reduce error, and the implementation of RBC has negligible impact on total ALD. Also, we see that DA has a significant improvement for nearly 5 days to the free forecast. For our future work, we will continue our background error tuning experiments with the latest updates in GoCast model and emissions, and we will need to finalize our BC configuration and observation usage in GC DAS to prepare for our analysis and retrospective runs in upcoming months. So thank you. I will stop here and happy to take questions.
Thank you, Yiping. We have one question online. Yeah, go ahead.
Yeah, one question online from Barry Baker. What other observations should we consider for future data sources?
We should. So our plan is to maybe also include the geostationary observations.
We have a little bit time. Any other questions? Sarah? Microphone is behind you.
So your system is based on loosely coupled system like GSI for atmosphere and JDI for aerosol. So I'm wondering, in your future upgrade, do you plan to really have fully tightly coupled where atmosphere aerosol was jointly simulated by JDI?
So do you mean that the atmosphere will also use the JDA? Yes, but so actually our system, DA system is independent from the GFS DA system. And it's expensive to forecast the aerosol species. So we plan to separate the GCAPs from the GFS.
Okay, thank you. Yeah, the next presentation again will be given by Barry Baker. Barry.
Yeah, can everyone see this? So yeah, I'm going to be talking about Nexus, or the NOAA Emission and Exchange Unified System, version 2. So we've been working on this for quite a while. So as I mentioned previously, we're developing this new CAD/CAM, and as part of this, chemistry models are inherently reliant on external forcings, mainly for anthropogenic emissions, as well as some other sources. But and so we need a flexible system to be able to add these emissions dynamically and for the various complexities, whether that's whatever grid that we have versus whatever chemical mechanism that we are doing. And so that's where Nexus comes in. Nexus is currently used in an offline presence operationally right now within AQMV7, as well as making its way towards being utilized in GCAS version 1. And so for instance, in GCAS version 1, we take the global emission monthly data and apply diurnal profiles, regrid to our modeling grid, etc. And so for those that are interested, you can look at Haiping Lin's paper, which we were a part of in 2021. And so Nexus at its core uses the HEMCO, or Harvard emission component, as its core model. HEMCO also allows for various what they call extensions to compute different emission schemes. So for instance, they have things like sea salt, dust, soil NOx, lightning NOx, etc. And the idea is that we can actually extend Nexus and HEMCO to use the same routines that we are developing within CAD/CAM to be able to do offline emission development. Let's just say emission process development, because the idea is that if we can use the same code and same infrastructure, then we can actually continue to develop both online and offline for these systems. So like one of the benefits is for instance, for dust, you want to make sure that your yearly dust emission is, within a certain range, roughly 1,000 teragrams a year or something like that, right? And so being able to do that in an offline presence, you can do it very quickly versus having to run the full model, full atmospheric chemistry model, where it could take a long time. And so what HEMCO does is it takes different modeling inventories, this could be global or regional, blends them together into a common grid, and applies masks and scaling and all these types of things. And so at the end, you get a model-ready emission for whatever grid that you have and whatever chemical mechanism that you have. It allows for easy configuration through data sets and variables, so you can add all kinds of variables, emission data sets, add different scalings and different masks, as well as add them to different collections and orders, like with the order of operations type of thing. So this is one of the main reasons why we're leveraging HEMCO, is because it gives us this flexibility, and it's a majorly supported system, already supported by Geoschem as well as NCAR for CESM. And so we're basically piggybacking on this, but tailoring it towards our configurations within the UFS. So this is the planned Nexus implementation as a Nexus or NUOPSI component. So in green, you could see what this would end up looking like. We would have the Nexus gridded component, where it basically wraps the HEMCO through a new ESMF interface, one that is not dependent on Maple. And it allows us to interact with the core and diagnostics. The benefit of this is that this also allows us to run it both online and offline through basically very similar systems. So you can do it either through the UFS or through the UFS as a Nexus only application. And so we've been working on this, and we're hoping to be able to get a PR done by the end of this month to be able to add this to the UFS. And so one of our ideas is to be able to use CDEPs, which is part of the UFS currently. We've extended this to have a new data emission component under CDEPs that allows us to input data directly from this highly supported essentially file IO component that's already within the UFS. So the advantages of using Nexus, so this is kind of the before and after picture. So previously, each emission inventory had to be directly ingested for this very specific model. This also means that essentially emissions were prepared ahead of time on the model grid for the chemical mechanism. And this basically required like huge amounts of data storage. So if you wanted to run 20 years of data, you had to have 20 years of emissions generated. And you can imagine this could be a very, very large data set, depending on how many variables you have, the size of your grid, etc. So after using Nexus, this simplifies our emission processing for the UFS. It offers the flexibility for global and regional applications, leverages our community, and everything can be basically developed at runtime through a configuration file. And it provides, robust model-ready emissions already, as well as diagnostics on those emissions that we can use to look at later. Some of the future things that we've been working on is MET-driven emissions. So this is where the extensions could really come play a role. So for certain type of sectors, there's a lot of reasons to think of weather-driven emissions. So for instance, mobile emissions, it's highly dependent on the outside temperature, as well as things like livestock ammonia emissions, or you could even imagine like wood fire burning within the US. If it's not cold, people aren't doing these things. And so it's a way for us to be able to take these inventories that are developed on specific years and apply them to other years dynamically. We've also been working to improve biogenic emissions. And so we've been updating the Megan version 2.1 within HEMCO to add multiple different things, namely simplified canopy effects following the Silva et al. Paper. And so we've seen some positive effects on ozone distributions as well as the isoprene emissions within the southeast. And so I won't linger on this, but the idea is that we can use this for UFS Chem to be part of that overall system where CAD-CHEM and Nexus can work together, as well as through various data assimilation and evaluation techniques. And so I'll stop there, and thank you.
Thanks, Barry. We have time for questions. Lee, the microphone.
Thank you, Barry, for this nice talk. So I have a question about the fire emission part. Today there's a talk given by Petro about the fire behavior model. So he also mentioned that in the future they will also provide something with emission. Do you think like this fire behavior model may be possible, like merge some function or connect with this Nexus system? Thank you.
Yeah, it could. We could also have, a different emission source through the fire behavior model. One thing I'm a little bit worried about with the fire behavior model is they're essentially running on like a 100-meter grid, and for a lot of our applications, that's very, very high resolution compared to what we're running on any of these operational models, right? So I mean, even the RFS is running at 3 kilometers. And so, yes, the short answer is yes, Lee. We could have the fire behavior model providing emissions and have this come in as a external data source to Nexus and do the speciation either within that, or we could do that within CAD-CHEM itself. We have options here, right?
Other questions, maybe online? No. Maybe someone has a question regarding Barry's first presentation about this CAD-CHEM development, because we didn't have time for questions. If not, thank you, Barry. Let's move to the next presentation. It will be in person. Jian He from Chemical Sciences Laboratory of NOAA, and also CU Boulder series.
So today I'm going to talk about adding gas phase chemistry into the global UFS for air quality. Here for their help and support of this work. So the motivation of this project is to enhance...
Get a little closer to the mic.
Oh, sorry. This sounds okay? Okay, great. So the motivation of this project is to enhance the UFS capability for global air quality forecasts through this development of a unified chemistry component. Here we named as configurable atmospheric chemistry, CAD-CHEM, that Barry and Kate has introduced in their early talks. The specific goal for this work is to link emission to atmospheric composition in a more comprehensive way to allow for global air quality forecasts and research application. So building upon GSL's go-kart aerosol model that Kate has introduced earlier, we incorporate GFDL's AM 4.1 chemistry into CAD-CHEM version 1.0 to have a detailed stratospheric and tropospheric chemistry. This process will also include additional aerosol composition and the online calculations of lightning NOx emissions. In addition, we have also included additional wet and dry depositions for those additional gas tracers and aerosol species as well. So, the model has been configured at C96 resolution and ran for 2016 to 2017. We use CES version 2024 emissions for anthropogenic sources. 5 emissions come from GBAC version 5. In this case, we do not have online calculations for biogenic emissions. Instead, we prescribe biogenic emissions from AM4 model and CHEMS model. But in the future, as Barry just mentioned earlier, we will have the online representations for biogenic emissions. The model has been also comprehensively evaluated against a variety of oppositional data sets. So let's first take a look at the photochemistry, which is an important pathway that affects atmospheric composition. The left panel shows shows an example of photolysis of NO2 comparison with ATOM observations. The blue line represents UIFCW25 simulated photolysis, and the gray line represents ATOM observations. The 4 panels shows the comparison over different seasons within both hemispheres. As you can see, the model is doing quite a good job in capturing the seasonality here and also the vertical distribution. On the right panel shows the OH radical comparisons. OH is an important atmospheric oxidant that determines the lifetime of many trace gases. This is a comparison showing the 4 ATOM periods over the northern hemisphere. Also, the model is generally can reproduce the observed OH concentrations here. This gives us some confidence that the photochemistry is reasonably well represented in the model. Let's take a look at ozone, which is one of the most important atmospheric tracer for the global air quality application. The left panel shows a comparison of zonal mean ozone distribution between GFDL AM4.1 model and the UIFCW model. Here we just trying to have a general check, a quick check how ozone is simulated in the model and if it is reasonably well represented in the model. So as you can see, sorry. So as you can see, the zonal distribution are quite comparable between the two. Sorry about that. As you can see, the zonal distribution is quite comparable between the two models. So we then take a closer look at the ozone profiles and compare with the ATOM observations, which is shown on the right panel here. So if you, I'm sure most of you are familiar with the UFS model, and there is actual default option for the GFS ozone photochemistry in the model. Here we are compare ozone profiles with explicit gas phase chemistry shown on the upper panel and with GFS ozone shown on the lower panel. As you can see, the large high bias from ozone, GFS ozone have been substantially reduced in the ozone with explicit gas phase chemistry here. This suggests ozone is reasonably well represented in the model. So if we look at the global scale, this is another example of tropospheric ozone comparison among the OMI MLS satellite observations and the UIFCW and the GFDL model. So spatially, you do see some consistent low bias, especially in the over the high latitudes, partly due to some uncertainty in the precursor emissions or some large-scale circulations and some chemistry as well. But generally, UIFCW is quite comparable with GFDL AM4 model, and particularly across different latitude bands here, you can see the seasonality is well captured in the model as well. So if we take a closer look at the regional scale, here shows a comparison of surface MDA ozone over different regions, over Europe, East Asia, North America, and South America during the summer season and the winter season. The blue dots represents the explicit ozone chemistry, and the orange dots represent the GFS ozone. So you can see this is oh, sorry about that. As you can see, this is a one-to-one, dash line shows a one-to-one line here. What you can see here is ozone with GFDR's AM4 chemistry actually doing a quite good job, much better job than GFS ozone in terms of simulating the surface MDA ozone, both in the spatial and the temporal dimensions here. So we do see, thank you. So we do see some model bias, as I mentioned earlier in the ozone evaluation, partly due to some uncertainties in the precursor emissions. So in the next few slides, I will show the precursor evaluation against multiple satellite data. So this is an example of comparison of tropospheric CO columns between MOPID CO, UFS, and GFDL model. As you can see, in general, model is quite comparable between UFS and GFDL model, but we do see some hotspots, like over the Africa here, which is mainly associated with fire activities. This suggests some potential overestimates in the fire emissions as well. So in addition, similarly, we also checked the seasonality of the tropospheric CO across different latitude bands, and the model is doing quite a good job here in terms of the seasonality. This shows another example for tropospheric NO2 comparisons between NOAA SMPP satellite and UFS scan. So at the global scale, the model tends to have to show some low bias, especially over the populated regions and industrial areas, suggests some low, potentially underestimates in the primary emissions. Similarly, we see the high bias over the Africa regions that suggests another possibility in the overestimate in the fire emissions as well. So we also look at some remote background regions over continents. In general, model tends to show some low bias there. This is likely due to some uncertainties in the soil NOx emissions as well. Currently, we kind of prescribe the soil NOx. I didn't show the detailed analysis here, but the comparison suggests there is some potential improvement in the soil NOx representations in the model. So this is another comparison for formaldehyde. Similarly, we do see the low bias over most of populated regions and also the industrial areas, and also in some remote areas. One explanation here is, as I mentioned, the biogenic emissions are kind of prescribed in this work, which could potentially lead to some uncertainties in the remote formaldehyde underestimates. And in CAD/CAM version 2, we are trying to have these online calculations. Hopefully, can address this low bias issue. Again, the comparisons are similar, show this high bias over the Africa and South America, which are likely associated with uncertainties in the fire emissions as well. So again, the GFDR AM4 chemistry is kind of designed for the chemistry climate applications and depends on different the different scientific questions you want to address. We can have more complicated, sophisticated VOC chemistry introduced, which could be done in version 2. So to summarize, in general, we have good confidence in the UFS model with AM4 chemistry here, and the model evaluation also suggests some potential bias in the precursor emissions and also uncertainties in the process level repetitions. These can guide us for the future model development through CAD/CAM version 2. So I will just stop here. Thank you.
Actually, we have time for one quick question, if there's one. No. Yeah, thank you. The next presentation will be given by myself. Let me see. My name is Ravan Ahmadov. I am a physical scientist at NOAA Global Systems Laboratory located here in Boulder. And I want to acknowledge many of my colleagues, also collaborators from ARL, EMC, and many universities which are listed here, and other organizations like EPIC, but it's quite possible I wasn't able to include everyone here who provided data or helped with this project. So I'm going to talk about some recent updates to the RFS smoke and dust model, and show some results from our evaluation for this 2025 ongoing fire season in North America. And as you know, over the last several years, at NOAA, we have been transitioning to a new numerical weather prediction model. Here you can see domains of our existing operational rapid refresh and high resolution rapid refresh model domains. And these models are still operational, will remain to be operational. However, there is a new model now, which is experimental currently, but it is approved for operational implementation. It's called Rapid Refresh Forecasting System. We have added smoke and dust prediction capabilities to this model. There are many advantages of this new model. One is this single high-resolution domain, which covers a very large region of the entire North America. And this is also, this provides us with huge advantages, such as, for example, to capture smoke transport from Canada and Central America into the US. And how this RFS model is designed. This is a very complex, busy slide, and my colleague Ming, who presented the data assimilation system of this model at this workshop. I won't have time to talk about all these details here, but briefly, there's a complex, very complex meteorological data assimilation system. Every hour, a new forecast is initialized by assimilating the latest meteorological observations, but also we ingest the fire radiative power data from so-called RAVE product. I will talk about that in a minute. So this is another advantage of this NWP system. If there's a new fire or fire is flaring up or dying down, we are able to get that information into the model with a short latency. So this is a diagram which describes this regional ABI and various fire emissions data set or inventory. There's a paper by Fangjun Lee. Here the reference is provided, which describes this product in detail. Just briefly, I want to highlight the inventory, the data set, FRP and emissions data set is based on the GOES and various fire detections. And every hour, again, this data is ingested into the model. So by ingesting this data, we can simulate 3D transport of smoke. What is smoke is primary PM2.5 from biomass burning, which could be wildfire or prescribed fire or agricultural fires. So this is a smoke prediction for just about 10 days ago over the North America. As you can see, there were many intensive fires burning in Canada and also parts of the western US. Here on this slide, I described main features of this model, also updates. Again, I won't have time to discuss all of them in detail, but one of the updates is this. So we have now actually 2 dust aerosols in the model, fine and coarse. And then the forecast length, this is again new like improvement, is 84 hours, 3.5 days. So 4 times a day, the forecast 0006 every 6 hours. Those cycles, their forecast goes out to 84 hours. And then another significant update is this updated new version of hourly wildfire potential index. I will talk about that index more, and it is provided to the users, but also this index is used to predict wildfire emissions. You can find all our forecast products, so right now it's experimental, on this website, public website. So what's HWP index? It is a new fire weather index where we take advantage of this convection allowing model like RFS or HER. It is diagnosed based on air temperature, humidity, soil moisture, and so on. It provides us with such an index, weather-based index, to basically, for example, to expect, for example, if wildfire will flare up or will die down depending on weather conditions. Of course, there are other factors such as fuel loading, dead fuel versus live fuel, or terrain, which also affect fire activity, but I won't talk much about that. And obviously, all these indices have limitations, but again, it's hourly index. And there's a paper by my colleague, which is published in Weather and Forecasting Journal, which describes this index. This is one of the forecast examples of this index. Again, the same day, August 31st, you can see almost like in the entire western US, but also, as you can see, these parts of Canada, like Arctic region, is under like high HWP kind of fire danger zone, where we have had many wildfires this summer. And if you go to the NOAA.gov website, maybe they changed, but just last week, this paper by James et al. Was highlighted, and this index was highlighted in by NOAA media group. Now, how we use this HWP to predict fire emissions? Here we use the FireX dataset, FireX field campaign, which was conducted during summer 2019. Provides us with a vast amount of measurements in situ, remote sensing, and surface aircraft. So we use this campaign, the data. Here, the fire that we studied in detail simulated this so-called Williams Flash fire, which was burning in the state of Washington. And so, as you know, to estimate fire emissions, we use fire radiative power from the satellites. The black line here shows the RAVE-based FRP time series. We can say it's ground truth. Of course, it has limitations due to clouds and, for example, dense smoke. So if we use persistence approach, which is this red line, here you can see the time series. Basically, we take yesterday's FRP and apply to the next day, because we need to predict fire emissions somehow. And there's no easy way to do this, given all these uncertainties. Now, the predicted emissions, this green line is based on the previous FRP history and also hourly wildfire potential, which can be predicted by the model because it's based on the meteorological variables. So we can now overlays the HWP map, this HWP time series, this dashed line, this gray line, and the magnitude is shown here. It's a unitless index, so higher means there's more like high fire activity we can expect, stronger fire activity we can expect. So if we focus on one of the days, this is August 8th, this is in UTC, so this would be late afternoon, evening time, local time in Washington. And you can see that based on HWP, our method says actually there should be more fire emissions when the persistent approach obviously won't capture this because it's based on previous day's FRP. And now, again, what's nice with the FireX campaign, it provides us with this valuable in situ measurements taken by aircraft, where they, this is an aircraft like photo. At this like pressure level, you can see about 600 millibar. The aircraft was flying and going into and outside of smoke plumes and measuring smoke or aerosol concentrations. Excuse me. Yeah, so here you can see, so this is so-called curtain plot, height versus time. This is for persistence approach. This is for the predicted FRP approach, where again we estimate the emissions using these two different methods, and then simulate, conduct retrospective simulation. The result for aerosol concentrations is given here. You can, the black dots show the measurements, where, as you can see, the concentrations exceeded 1,000 micrograms, very dense smoke plume. And the red line, you can see, maybe it's a little bit hidden, and then the green line. Obviously, as you see also these bias statistics, the green line, the predicted method is much better. It can significantly outperform this persistent approach. Again, based on our HWP based prediction. And now by using this method, we can forecast smoke, like near surface smoke, and this is one of the days in June when smoke from Canada was transported into the Midwestern and also eastern parts of the country. I won't have much time to talk about this. This is AOD comparison. I encourage you to check this poster by our summer intern, Anna Maria. I think the poster is still on the wall. It's next to the entrance. So this shows time series, hourly time series for 1 month's time period in June. So Edmonton and Saskatoon, big cities in Canada. How you can see how good the model was able to forecast those very high PM2.5 concentrations. So I need to finish my talk because I'm out of time, and thank you for your attention. George Mason University.
Thanks, Ravon. Can you hear me okay? Okay, I hope you can hear me. Yes, today I'll be presenting on advancements in NOAA's Unified Forecast System Air Quality Model, or UFS-AQM, to improve our nation's air quality forecasting capabilities. This is a large collaborative effort, and I'm presenting really on behalf of the entire NOAA ARL EMC UFS-AQM team, all affiliates, and many more. To provide a quick background, the National Air Quality Forecasting Capability, or NAQFC, is largely based on NOAA's Unified Forecast System, UFS, and its Integrated Air Quality Model, also known as UFS-AQM. It provides daily forecasts of surface ozone and PM2.5 concentrations, as well as smoke and dust, up to 72 hours in advance across North America. the initial implementation of online coupled AQM version 7, or AQMV7, was in April in 2024, and this was a major milestone in operational air quality forecasting, being an online framework and also enhancing the wildfire air quality impacts. In this presentation, we will provide an overview of several key upgrades being developed for the upcoming AQM version 8, or AQMV8, and the full year 2023-2024 prototype experiments with updated chemistry, processes, emissions, and also physics, and that's slated for operations in 2027. So NOAA's operational UFS AQMV7 is based on online coupling of the UFS-based atmosphere model with the FE3 dynamical core with CCPP physics, that's on the left diagram. This is integrated in time step with the full complex chemistry using the air quality model, or AQM component, on the right diagram, which is essentially an ESMF compliant wrapper using NWAPC driving the community multi-scale air quality model, or CMAQ, handling the complex chemistry, aerosols, and other chemical and transport processes. And one of the major updates we've accomplished in the UFS AQM recently is to its chemical component, again known as the US EPA Community Multi-Scale Air Quality Model, or CMAQ. Shown in the diagram on the left in the red boxes are all the processes that CMAQ handles in the AQM, which is extensive across ingesting detailed anthropogenic and natural emissions, complex gas and aerosol phase chemistry, photolysis and dry and wet deposition, and removal of chemical tracers and aerosols. However, the current CMAQ model in the operational UFS AQMV7 is based on version CMAQ 521, which is rather old. This was released over 7 years ago in June 2017. And we at NOAA have updated the AQM chemical component from CMAQ 521 to 5.4 to reflect a more state-of-the-science chemical model. And this was significantly challenging and resulted in major code and science changes. We are also updating the anthropogenic emissions using a high-resolution data set based on the Neighborhood Emission Mapping Operation, or NEMO data set. NEMO was created based on research and development from George Mason University using highly detailed geographical data sets and spatial surrogates shown on the left, using different sources and allocations to create model-ready emissions depicted by the center diagram here. This is applied across 9 anthropogenic emission sectors using the US EPA National Emissions Inventory, or NEI, for base year 27 and updated currently to reflect year 2019. And as shown on the animation on the right, using the high-resolution NEMO at 1 by 1 kilometer spatially has the ability to much better represent the fine granularity of emission sources as compared to currently used coarser emissions data sets, say at quarter degree or 0.1 degree currently used in the AQMV7. And I believe Daniel Tong has a presentation next on expanding this to a global 1 kilometer data set. And an example of the impacts of updating these regional NEMO emissions is shown here, compared to the currently used emissions in AQMV7, which is based on a coarser data set based on 2016 emissions. Here we show the comparison or difference plot for nitrogen dioxide, or NO2, on the left, and sulfur dioxide emissions, or SO2, on the right. And while I didn't mention, since there's limited time, is that we're also updating the global anthropogenic emissions using the NOAA Emission and Exchange Unified System, or NEXUS, that was discussed by Barry earlier in the session, for both updated sources, speciation, and also here time-varying weighting factors applied to the global emissions across the North American portions of the UFS AQM grid. And this just I want to highlight here the result is large changes in emissions, widespread decreases, and some increases that vary with time. And an example result here of updating these emissions and impacts on the AQM is shown here for the average of the first model layer differences for ozone in the first week of August of 2023, and absolute differences in ppb on the left, with relative differences in percent of ozone on the right. And just depicting here, the results show widespread decreases in ozone up to 10 ppb, which is significant, or 33% decrease across both the West and East US in our developments for the next AQMV8. And I just wanted to highlight one challenge in the past development of the AQM historically is configuring the science-based R2O development and effectively tracking these developments using continuous integration and establishing consistent prototype or i.e. experimental simulations based on defined retro periods and case studies with consistent evaluations. So now all developments here from ARL of the AQM and our supporting affiliates are going to be well documented, tracked, and evaluated using these established prototype simulations. Where here we're beginning with prototype 1 over a full retro period of May 2023 to April 2024 for our AQM V8 P1, prototype 1 versus the current operational AQM V7. The main updates here shown in bold in the table and described earlier are updates to the chemical component, the CMAC 5.4. We have the updated high-resolution NEMO emissions, updated global emissions, and further updates to the RAVE fire emissions. Ravon talked a bit about the RAVE product before, but it's the satellite-based near real-time hourly biomass burning emissions that are fed into this AQM system and are critical to forecasting the air quality impacts. The focus on the results I will show next here are only for summer 2023, while we have the results for the full year. And again, the major changes are shown in bold here in the table. So shown here are some results based on average July 2023 spatial bias plots. That's the model minus observation versus the ground-based US EPA Air Now ozone observations, with the blues indicating negative biases and the reds indicating positive biases on the left. Where the AQM V8 P1 simulation does show significant and profound improvements in reducing the overall summer ozone overpredictions that are rather systematic in the eastern US with this system in the bias plot in the bottom left compared to the current AQM V7 on the top left. Where on the right, we show a normalized mean bias scorecard across different EPA regions, also for urban versus rural on the y-axis versus time on the x-axis. And the red colors here indicate that there's significant improvement for AQM V8 versus AQM V7 in normalized mean bias scores, with the blue colors indicating some degraded performance in some regions and times for the AQM V8, but the majority of the regions and times we see more red colors here, indicating significant improved ozone performance in AQM V8. And I don't have time to go into much of the detail, but the changes are due to multiple reasons from the updates as described previously for the AQM V8. The reduced NEMO emissions of ozone precursors such as NOx leads to overall lower ozone and helps reduce overpredictions. We have improved halogen chemistry and rates in the updated chemical mechanism in CMAC 5.4. These also help lead to further ozone loss in coastal regions, helping reduce those overpredictions. And also we have enhanced dry deposition of ozone to the soil surfaces, particularly more sensitive to soil moisture in the western US, and that impacts biases there. Looking further into the results and evaluation of the chemical changes by comparing AQM V8 and AQM V7 against the summer 2023 aroma campaign, in the example here of the June to August 2023 aircraft flights by the DC-8 in the west. This shows XY scatter plots for ozone versus NOZ on the left and NOx versus NOY in the center. And what we're showing here is that the AQM V8 in green dots is closer to the observations than that one-to-one slope in black compared to AQM V7 in blue. And what this means is that the AQM V8 reduces its overpredicted NOx to NOZ conversion rates, which then leads to smaller underpredictions in ozone production efficiency. And then that enhances ozone production and helps address some of the ozone underpredictions that we actually see in Central California in AQM V8. Further looking at results and of the evaluation of the average. What's that? 1 minute? Okay. Further looking at the results and evaluation of the average July 2023 time series in CONUS. Here I just wanted to show that for these time series and the ozone on the top left, we do see improved performance with overall improved statistics across the board on the right. But in the PM2.5 in the bottom left, we might notice that in the green line, we're actually lower. And this actually exacerbates the underpredictions we see in PM2.5. And this is impacted by larger dry deposition in the AQM V8. And that leads to, again, lower PM2.5 background and larger underpredictions in this case. And looking further into PM2.5 and evaluation of AQM V8 P1 and speciation during larger fire periods in late August of 2023, we do find that while the AQM V8 does pick up the total PM2.5 quite well for these western fires reasonably well, the speciation evaluations show that there's uncertainty in the fire emissions, particularly like in NOx and PM2.5 nitrate formation, and also results in overpredictions downwind to the east for PM2.5 species like nitrate elemental carbon and organic carbon shown here. So thus AQMV8 has some uncertainty in the rate of fire emissions and transport, and we need to do further improvement there. So in summary, we've developed and tested several key upgrades to the UFS AQM operational system and created a full year 2023-2024 prototype simulations for the next AQMV8. And the AQMV8 P1 prototype simulation with updated chemistry and processes and emissions do show improvements in simulating boundary layer ozone compared to the current AQMV7 operational model during summer. But there is uncertainty that remains in the AQMV8 simulations of PM2.5, and we have large impacts from increased dry deposition on the background, and also fire emissions and transport and PM2.5 do need further improvement.
We're at time.
I will just be brief. You're at time? Okay, I'll be brief just to say that we are currently running future ongoing prototypes to update the physics to GFS 17. There is significant sensitivity between the meteorology and the air quality, and we're doing improved spin up and physics tuning simulations for the next AQMV8 prototype simulations with updated physics. And we have a lot to do.
I'm sorry,
for
we're
the
at
future
time.
prototypes. Okay, thank you. I'll just wrap it up. Thank you. Any questions?
Thank you, Patrick. So the next presentation will be given by Daniel Tong from George Mason University.
Good afternoon. Patrick, if you can stop sharing, I can start sharing my slides. Thank you. I wish I could join you here, but yeah, I appreciate the opportunity to share some new projects that we are experimenting. So Barry both Barry and Patrick laid out the background on the importance of emission, and then also the plan that we are working on to support the UFS atmosphere composition modeling. So this is actually a new effort that's complement this effort has been going on at AIL, EMC. So you can see the work Nexus is working on is to use gradient emission data sets to generate a model-ready emission data set. And this work is working more on the back end, trying to work directly with emission inventories and generate graded data that can be ingested by Chemical or Nexus. So this work is contributed by Siqi Ma and Hannah Fang from George Mason. So why do we need a 1 kilometer emission, high resolution emission? I think there are many reasons. I'm not going to emphasize here. So just like goal here really is trying to develop this new technique that we can allocate a high emission data set to very high resolution, including hourly and also 1 kilometer. In this case, I talked to Barry and other people. They think that directly working with the original latitude longitude it will be the best to support both regional and global models. So the goal here is to develop this method to generate a global NEMO. Okay, I want to start. So Patrick already covered this. I just want to say that we have a lot of community applications for this 1 kilometer data set. It's huge. As Barry mentioned earlier, one day's data is about 7 terabytes to generate 1 day's NEMO data set. So it's really huge. We have to aggregate and merge it together so that the rest of community can use it. But it did gain some benefits if you really want to look into a high resolution and want to more accurate spatial interpretation. So all the emission data sets are the same, except they are different in 4 ways. The first, you start with the raw emission inventory you use, right? You can use EDGAR, you can use SEAS, but EDGAR, of course, is using a bunch of emission inventories. So there are raw emission inventories. That's the starting point. They are basically, it's one number per country or per county per year, right? So that's how you get started with. And they're also different in 3 other ways. How do you distribute them spatially, right, into different grid boxes? And that also including the spatial resolution. And how do you distribute them chemically and also temporally, right? So that there are the 4 major differences for any data sets. This is the same method we use to develop the national NEMO. but except this is getting more complicated when you work with a global data set for two reasons. One is it's not all the input data you have in the US will be available, so you have to be creative to find a outlet method and data set to do that. And second is the data is huge, and it's memory problems and some resources, computational resources problems, and you have to also be creative to achieve that goal. So we started with Edgar because Edgar is a widely used global data set. It has 0.1 degrees, about 10 kilometers. It's sufficient for most of the global applications. But if you want to go to higher resolution, like for example, you want to go 3 kilometers, right? That may not be good enough if you want to have a full chemistry module implemented. So this is the starting point for us. We are also following the structure of Edgar's method and also trying to improve upon that. We basically are benefiting from the previous wonderful work done by the Edgar group. The Edgar groups, the data set, they have several sectors, just like we have for the national emission inventory, and they are following a method more close to the IPCC approach, and then also sees the same way, right? It's different from the national emission inventory. So lots of tools that we developed from smoke used for the national emission inventory have now had to be redeveloped or revised to make this work for the global data sets. They are generally dealing with two kinds of emission sources, that is aerial source and line sources. There are also point sources that we are treating as separately. So for aerial sources, mostly using aerial weighted, and line sources calculate the length and allocate that the total emission into each box based on the proportion. So the spatial technology used here are basically based on several tools.
Yeah, 5
the
minutes.
First one is the first one is XSMM. That's a Python package that's been widely used, including Hemco is using that to process emission based on the error weighted, and then also you have a mass conservation method, so it's not going to lose the data, which is a good way. But they cannot. The limitation of that is they cannot deal with some special sources like the road and the line, and also you have multiple polygons. That sometimes this tool just not good enough. So we have to combine this tool with ArcGIS and also Postgres. And this is another tool that we use to generate a different spatial surrogate. Spatial surrogate is basically the fraction that you use to allocate an emission into different grid boxes. So here's some example how we deal with the emissions. This is one example for agriculture, which is aerial source. You can imagine this is all polygons, right? So how do you generate the spatial surrogate for agriculture, right? So we are using, in this case, we are talking about manure management. So we have a map of animal density, right? That's actually very high resolution. But then also you cannot just simply use that because there's also some problems with this data set. So we are combining the animal density with land use fraction. And so that gives you this manure management proxy that you can use to allocate emission for this sector. Similarly, if we want to do agricultural burning here, this is a crop residual burning. So we're using land use fraction, and also we're using light because that sometimes you can use that to detect human activities. So this is a map we generated at 0.01 degree, and compare that to the 0.1 degree from Edgar. It's not much different, except that you have to zoom in to see the difference. As the one that Patrick showed earlier, you have to go to the local scale so that you can see the differences here. But you do see some differences, like here, this for ammonia and NOx. And if you really look into that, you can see the scales are different because the global NEMO should be 100 times lower than the Edgar for each box. And that's also, you can see bigger difference if you look at agricultural waste here. So if you look at the aggregate for NOx and OC over the United States, it's pretty much covered for the entire U.S., the continental U.S.
You got 2 minutes.
If you're using this new approach, we can see that the agricultural burning was mostly confined in the eastern part of the country, not for the entire U.S. But this is still just like a very rough comparison. We think we should dive into that to look at the details and to verify which method is better. So another good example looking at is for transportation, which is very challenging, right? In the U.S., we have 3 types of roads: highway, freeways. We have level 2, and then also have country road. So we enjoy the luxury of this richness of the data. But if you work in Africa, in South America, you do not have that kind of data, right? So the way we are doing right now is we are trying to use OpenStreetMap to get the road map mask, which is at the lower column, and then combine that with the satellite nighttime light, density, right? So hopefully we can come with a better spatial proxy than just using one. And you come up with the spatial proxy on the right. So applied this method to this global NEMO, and we compare that to other benchmark data sets. One is Edgar, another one is the NEMO, and then at the bottom is the global NEMO. If you look at the Edgar map, it's actually amazing. It's captured all the major highways pretty well. But because the limitation of this spatial resolution, you can see that if you are going to final resolution, right, the highway probably will be extended to multiple grid. That can be wrong. It depends on your model resolution. And NEMO, of course, this is the standard way to do it. But again, this is only for the US. We have the data available. And if you look at a global NEMO, it's not like Edgar. It's not like NEMO, but it's something between the two. And that's because the data set that we have. So this is a new method that we are trying to compare to the traditional ways, and we hope we'll have more time to look into the details to see the impact on emission allocation. To summarize,
we're at time.
We have developed this method for high-resolution global emission mapping. And right now, this is still work ongoing. We welcome collaborations. And in the future, we're trying to verify the mapping method with benchmark data sets and want to complete all the emission sectors so that we can make this useful and also support the multiple chemical mechanisms. I will end here. Thank you.
Thank you, Danielle. Yeah, unfortunately, we don't have time for questions. I encourage you to contact Danielle and other speakers who, if you have questions. Next presentation will be given by Hai-Chin Lee, affiliated by NOAA Global Systems Laboratory and CU Boulder Series.
My topic is the aerosol dependence of the community convective cloud C3 scheme in NOAA's UIFS weather model. So we will talk about the aerosol interactions with cloud physics. So the motivation is that the National Weather Service in the United States, EMC, is already using the Thomson macrophysics scheme, which can be used both double moment and aerosol aware. The Greer filters and the new C3 scheme can also be tested with aerosol awareness. The simplicity of the resolved and non-resolved approach would allow to include the direct and indirect effects without much additional computing time in operational applications, assuming with acceptable performance. While the original Thomson macrophysics approach derives necessary aerosol variables, say water-friendly aerosol and ice-friendly aerosols, from cosmologies. We use prognostic aerosol emission to derive more realistic real-time aerosol distributions. In addition, the direct effect is already included in the operational health smoke under the real-time rules version 1, which will be operational next year. While there's still much uncertainty in treating the indirect effect, we hope that when the atmosphere is either very polluted or very clean, we would get a positive response, say, improving the forecast from the direct and indirect effect, even in operational configuration. In part 1, we will briefly discuss aerosol indirect feedback with microphysics. In the Thompson microphysics, the hygroscopic aerosol is referred as a water-friendly aerosol, WFA, and the non-hygroscopic S-nucleating aerosol is referred as S-friendly aerosol, FA. For Euro-Thompson applications, WFA and FA are derived using go-kart chemologies. Here, we embedded sea salt, dust emission, and biomass burning modules, as well as antiprogenic emission into the UIFS by using CCPP. The aerosol modules are directly called within the physics package. The prognose emission of sea salt and organic carbon are combined to represent the WFA emission, while the prognose emission of dust usually represents the FA emission. So the additional computing cost is just about 1%. We have two sets of experiments. One is the control run with the default configuration for WFA emissions with go-kart technology. Another is a new run with the prognostic aerosol emissions. We selected 10 boreal winter case in December 2020 and January 2021. I did notice that in order to distinguish the convection and microphysics effects, so we turned off the aerosol awareness in the GF convection. Since we turned off the aerosol awareness in the convection, we can see that most of the precipitation difference are from the microphysics, say resolved precipitation. We can, over the North American region and the Europe region, we can see that the significantly increased aerosol generates more small droplets competing to form. Okay, thank you. Yeah, thank you. So yeah, over this, the significant increase, the aerosol generates more small droplets competing to form precipitation, and they reduce the resolved precipitation. And over the Southern Ocean region, so the control run has very extremely low aerosols, and the moderate increase aerosol enhance the development of cloud water, and also generates more resolved precipitation. Yes, so when validated against the CPC rain gauge observation, we can see that the control run have a severe positive precision bias over North America and Europe. And these positive precision bias are significantly reduced by the new run with aerosol awareness. For example, over the Europe region, the observed precipitation is 1.31 millimeter a day, and the control run has strong overestimation of 3.06, and the new run significantly reduces to 1.34, quite close to observation. Over North American region, similarly, that the new run is more close to observation. We have published this work on GMD, and more analysis of the impact on cloud radiation intermediates are in this paper. So in part 2, let's discuss about the aerosol impacts on convective parameterization. To foster collaborative work across NOAA on convective parameterization, future development efforts are shifted towards the community convective cloud parameterization, C3. The C3's starting point is the GF scheme from top of the UIFS weather model. Currently, the major developers so far are George Greer and Haijin Li from NOAA GSL, Lisa Benston from NOAA PSL, Stavlo Freitas from MP Brazil. The current status is that Lisa added the updraft vertical velocity from scale SAS and prognostic sigma closure and cellular automata. We improved the coupling between convective class and the radiation, aerosol interaction with convection, and also the various approach for downdraft cold pool parameterization. The aerosol interaction with convection are implemented through two processes. The first process is the conversion of cloud water to rainwater in updrafts. So we use the CCN dependent conversion of cloud water to rain. Currently, we use a Berry conversion, but other approach can be easily implemented. Another approach is the precipitation efficiency for the downdraft. We introduce proportionality between precipitation efficiency and the total normalized condensate and evaporate. The precipitation efficiency is a key parameter determines the strength of the downdraft. So yeah, let's give this at the same time. Yeah, we also have two experiments. One site is a control run with a constant AOD with port 1.4 as non-aerosol awareness. Another is the aerosol run, which derived, I use the AOD derived from the water from the aerosol and the affinity in the Thompson method. I noticed that for this, we can see that the aerosol information is consistent between microphysics and convection. We selected boreal summer case in June and July 2020 with prognosed aerosol emissions in part 1. Here is the 120-hour AOD difference between the air run and the control run. The warm color indicates the polluted areas, and the cold color indicates the clean areas. For the precision efficiency between the aerosol run and the control run, we can see that over 6-hour instantaneous value and 120-hour, we can get we can see the air run has a low value over polluted areas and high value over the clean areas as expected. And for the 120-hour vertical integrated cloud ice difference between the air run and the control run, we can also see that the air run has a had more cloud ice over the polluted areas as expected because the convection is surprised and more cloud condensate detriment at cloud top above the freezing level. So yes, and we can see also that we have less convective precipitation over the polluted area and more over the clean areas. Yeah, when validated the total precipitation against the rain observation, we can see that the positive bias from control run over Central Africa, Southeast Asia, South Asia are significantly reduced by the aerosol run, and also a cloud fraction difference also affected. And so for the radiation, so for the control run has strong positive bias over Central Africa, South Asia, Southeast Asia, East Asia, and North America, and this positive are significantly reduced in the aerosol run. So yes, I expected that this is initial implication can improve the forecast for medium range weather forecast. So yeah, for summary, I stop here. So for some time for questions. Thank you. Yeah.
Thanks, Haichin. Maybe time for one quick question. Online. Here. Okay, thank you. Yeah, so last not least, presentation will be given by Emily Faber from University of Maryland.
I'm going to test this so I know how it works. All right, I'm going to kind of stand over this way a little bit so that I can actually see you guys over this podium. Like he said, my name is Emily Faber. I am a finishing grad student at University of Maryland, Baltimore County. And I'm going to show you a little slice of what I've been doing for my thesis work today. So it occurs to me that not everybody spends all day looking at images of dust. If you don't, I highly suggest it. It's really interesting. And that's what I do for basically a living. So mineral dust is really important to our climate. It affects radiative balance, hurricane formation, crops, everything from air quality to all kinds of things. It's the most prevalent aerosol in our atmosphere. If you were to take all of the aerosols out of the atmosphere at any given point, most of them would probably be dust. And a lot of them come from things called hydrological sources. So these are like alluvial sediments, sediments that have accumulated in areas due to like runoff and have had time to tumble around and become a little bit smaller, and that makes it a lot easier to actually get lofted into the atmosphere. So you can see on the right here, there's a vast array of different kinds of dust. You can see different colors and different shapes, different sizes, different scales, all kinds of fun stuff. So that kind of sets the tone for what we're going to be looking at. And so what I've done is designed a new sediment supply map, and I wanted to know, first of all, is this sediment supply map actually any good? Are we capturing things that we know to be true? Does it have a seasonality at all? And then I did actually plug it into the UFS, and so I'm going to show you some results of a first implementation model run, and we're going to see if the AOD is actually realistic at all. All right, so I would be remiss if I didn't tell you a little bit about how I make the sediment supply map. This is not super robust, so if you have further questions about like the nitty-gritty details, please come talk to me afterwards. Because what we do is kind of, so we take reflectance values from MODIS currently. We can do this with other systems, and it's at a 5-kilometer grid, and we can take several different wavelengths and combine them into different things. So you guys are all familiar with an NDVI. That's what's in that top right corner. And then if you have ever worked with MODIS before, you are familiar with the MODIS bit mask. That's what's in the bottom left for snow and ice, is this particular case that I'm showing. And we use all of these kind of pieces and parts to derive information about what type of sediment we're looking at and if it's covered in water or vegetation or anything else like that. So that's kind of what we're doing in the bottom right-hand corner there. That's what's called a HLS image. That's hue, lightness, and saturation. It's a different way of representing color. And you can kind of see in this image that it's really easy with your eyes now to pick out where the deserts are on the globe, because they're all blue in this image. So that's what we do, and we make a larger map that can go, that we make for a month. That's what's implemented in the UFS currently, so that's what I made, is a monthly representation of what we can get with a MODIS retrieval, which gets an 8-day average. So this is it throughout the year 2020, which is what we did for this study, and you can see that it captures like most of the variability that you would expect to see. So the deserts in the Sahara, the Middle East, the American Southwest, and even Australia all kind of breathe throughout the year, especially that Sahel region. So these regions, we were really excited to see that we're capturing things, which is what that first question was about, first science question was about, is we wanted to make sure that we were actually seeing things that were real. This is just a zoomed in view, so I wanted to make sure that like some specific dust hotspots were actually picked up correctly. So this is July on your left and December on your right, and you can see like the American Southwest is what I've got it labeled up there, but really it extends down into Mexico and some other areas, and you can see how it changes between July, which is peak dust season around that region, to December on the right-hand side, where there's kind of nothing. It kind of gets quiet there for a minute, and you can see the drastic change of the Sahel region, which is in the picture that I've labeled Beaudelet, because the Beaudelet Depression is right there in the middle. Another really interesting lake that we were interested in capturing is Lake Eyre, because this doesn't have a definite seasonal cycle. So like it might flood one year, and then it might be dry the next, and then it might not flood for 3 years. We don't know. There's also a lot of really pretty seasonality that happens in the Arabian Peninsula, and I was really interested in what was going on in Namibia because I know that this is a place that we usually miss some AOD episodes and models. So the setup for the model runs was actually very simple. We did some baselines, we changed something, and we see how it did. I ended up doing two what I'm going to call baselines. One is with a theoretical maximum, so I've set everywhere where there's bare land to a 1, so this allows emission in all areas. it might be controlled by something else like the wind speed or the soil moisture. That's fine, we're gonna see how it does. This is a theoretical cap on what the model is capable of simulating, so for like really big events, I'm not gonna spoil it for you, we should be able to capture the maximum AOD that we can see in observations. We did one with my sediment supply map, and then with the oldie but a goodie, the topographic source map. So it works, it comes out the other side, we implemented it correctly kind of thing. This was a great little movie to make because it actually like worked. I was very excited on this particular day in the office. And so you can just kind of see, this is the Godzilla dust storm. You guys remember from 2020, got picked up off the west coast of Africa. This was actually one of the biggest dust storms ever recorded. And it reached all the way across the ocean there, and it came up the east coast, as you can kind of see. So how did it do? The top figure here is the AOD difference, and I'm doing everything at 550 nanometers because we're looking at dust. And this is the difference between the sediment supply map, that's what the SSM is called, and my control, which is the ones. This is all blue because what I just told you about there always being a theoretical maximum value, we wanted to be able to make sure that we were actually capturing things. If for some reason some of this was red, then I probably implemented it wrong in the model, and I needed to go back and fix things. And it didn't, so that's very exciting. Then I just plotted also the percent difference down there on the bottom just to kind of get a better sense of how different that maximum was from the sediment supply map. There are little pockets of little blue places there. Those are convective cells that we think are contributing to that. So ultimately, the sediment supply map is behaving how we expect it to with respect to the idealized maximum. Next, I wanted to compare two actual observations. So on your left here is the MODIS, again, 550 nanometer AOD, and I have actually reprojected this. This comes down at 5 kilometer resolution, and I wanted it at C96, which is what I was doing for model SIMs. And I've cleaned it up and made it all nice and pretty for you. So this was really cool because you can see that plume in the observations and in the sediment supply map. This is a particular timestamp of the maximum of this particular dust storm, and you can see the spatial extent is very similar. The location of the maximum is very similar. We're very excited about this. So the SSM also behaves how we expect it, how we want it to, with respect to Terra, at least. All right, and so this is where I did some quick analysis for you guys. There's a more robust analysis forthcoming, and if you want to see it, please come talk to me. I'm here today, tomorrow. And I just wanted to quickly highlight the maximum. So I went through and found the maximum extent of this particular dust storm, the Godzilla dust storm, and on this day and this time step is the maximum. And in our baseline case with the ones, that AOD is 6.18. That's really high. We want it to be really high because we want to be able to make sure that our model can capture something that is that high. And then on the right top is the new sediment supply map that I implemented. This is, again, the maximum timestamp, and my map, the max produces a 3.52, which is really cool because if you actually look at the MODIS, the same timestamp, same time, the max of the Godzilla dust storm, this has been widely reported at 3.5, and actually I don't have it in this presentation, but if you pull the AirNet station data from Cape Verde, that's right there, Cape Verde, 3.5, my map, 3.5. Very cool. I also did a quick distribution because I wanted to see that. I know that there's been traditional issues with that. So on the left here is the MODIS AOD values, and I just put the frequencies. I threw out everything below 1 because that was mostly background, and I was interested in seeing like a lot of the plumes going on. On the right-hand side is the same thing, but with the sediment supply map that you just saw, and you can see like we're getting some of those peaks, but it trails off really fast, so those really high AOD values are still not as well captured as we would like them to be. I've got a couple pet theories about this. We can talk about that as well. But I will leave you with some conclusions here, is that we were able to actually make a new sediment supply map. It's for 2020. We were able to implement it into the UFS. It looks realistic. And then the AOD actually looked realistic on the other side, which was awesome to see, and that it actually did well capturing a big global event such as the Godzilla dust storm. So there's lots of future work that I'd love to do with it. We can also talk about that sometime. Thank you.
Thanks, Emily. We have time for questions. Lee.
You show a slide about using the new SSN compared to control run.
So maybe I didn't explain this map extraordinarily well. So this control is actually an absolute maximum. We want to be seeing that this is blue here. If I saw that this was red here, then I would be doing something very wrong in my modeling. So what we did was do that control run is at an absolute maximum. So everywhere on the planet's surface that isn't covered by water is allowed to emit at a maximum potential. So this is always, 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 if we're doing something correct, always going to be higher than the SSM.
Online question?
Yeah, for
Okay. Yeah.
John. It's from Patrick Campbell. It says, great to see your nice results on gas phase chemistry in UFS for global air quality. How well does the surface ozone compare to ground observations? Eventually would like to try model intercomparisons with UFS AQM to move forward towards future NAQFC, possibly using global UFS CAT-Chem. Thanks. Maybe also then for ground PM 2.5 concentrations.
Thanks, Patrick. So I showed this surface MDA ozone comparisons with TOR data sets. This is the only surface evaluation that I have done so far, not the hourly ozone or surface PM 2.5, which we could include it in the future. But based on the surface MDA ozone comparison, at least our model is, I would say, doing a quite good job in simulating MDA ozone across different regions that I showed over US, Europe, East Asia. And we do have a little bit of higher bias over South America, basically because we don't have enough TOR sites over there. So, but it could be easily done to include additional surface evaluation. Yeah.
Yeah, thanks, Jen. I suggest we continue this discussion during the coffee break. Let's thank all the speakers.
I do have one last comment. There's going to be a shuttle for the Mesa Lab tour, so if you signed up for that, it's going to be out there here right now, and then there's going to be another shuttle that'll come at 3:35. Also, they're going to be pulling tickets at 4:45 today.